my dear students, welcome to IMS Academy. Hi, I am Vipin Mishra, the lead mentor at IMS Academy, and I welcome you all in this smart revision series of IMS Academy. You know, no preparation is complete without a proper revision. Revision plays a vital role in every preparation, and that's the purpose of this series. So we are running with this series in which we will together we will revise the subject power system in this series. Okay. So as the gate exam is inching closer and closer day by day, now if you will be able to revise the complete subject within few hours, that will be like a treat to you, isn't it? Because power system is a very important subject. It has a lot of weightage. If we talk about the weightage of this subject, it has a weightage around 11 to 13 marks. And these are the topics from which you can expect gate questions. For example, fault analysis, load flow analysis, compensation technique, insulator cables and distribution, power system stability, performance parameters of line, power system protection. So power system has a very vast syllabus, and to revise it in minimum number of time is a very difficult task. So here we come with this series in which we will be able to revise this subject within 3 to 4 hours. So the complete revision of power system is divided into 3-4 parts. So this is the part number 1, and today we will discuss some topics, and then later on you can practice those topics, and then we will meet in another session and we will revise some other topics as well. Okay. So let's get started with the very first topic, and that I have chosen to be the fault analysis, which is very, very important. You can expect questions of 2 to 3 marks only from this particular chapters. And what are the important topics? The per unit system, symmetrical fault analysis, unsymmetrical fault analysis, and bus impedance matrix. So once again, I welcome you all in this smart revision series of IMS Academy, and let's get started with the fault analysis. So if we talk about the fault analysis, the first important topic is per unit system. So here we will be revising all important formulas and important points regarding every topic and every chapter. So per unit system, this is the first topic. So if we talk about per unit system, how do we convert a quantity into per unit quantity? So per unit quantity, okay, the per unit value is basically defined by actual value of a quantity when it is divided by a chosen base value, then we will get the per unit value. Okay. And we are often interested in converting the quantity from one base to another base. We have a set of base and we know what is the per unit value of that quantity in that particular base, but we want to convert that per unit quantity into some other base, isn't it? We need to do this type of conversion, specifically if we are having transformer in the line. So with transformer, the base also transform as per the transformation ratio. So we need to convert one base quantity into other base quantity. So for that we have a formula. So if suppose we have an impedance Z1 per unit in one base, and we want to convert this impedance into Z2 per unit of other base, then what is the formula required for doing this task is Z2 per unit, this will be equals to Z1 per unit V base 1 over V base 2 square into S base 1 over S base 2. So this is the formula where what one denotes the old base and 2 denotes the new base. So this is a very important formula. And also we have another formula. If suppose we have to calculate Z base, then Z base is equals to what? V base upon I base, and if we multiply V base on both sides of numerator and denominator, we will get V base square upon S base. This is also one of the formula. And why we are talking about this formula? Because sometimes we will be converting one impedance from one base to another base like this. Z per unit, this will be equals to what? Actual divided by the base. Okay. So if we just put the value of base which we have calculated here, it will become Z actual, and when you will put the value of Z base, it will be S base upon V base square. So that will become the formula. Okay. Now this formula will be specifically used for transmission line impedance, okay, for converting it from one base to other base. So just see, these are the important formula for converting one base to another base, how to calculate Z base and how to calculate Z per unit by using one base voltage and base MVA, okay. Now what are the important aspects of power per unit system? With per unit system we are having so many advantage. For example, if we have transformer and you have calculated the things on the primary side, the same result is valid on the secondary side as well. Then the biggest confusion that we have in electrical engineering is regarding the star and delta quantities, star and delta system with the line and phase quantities. But if we are using per unit system, the calculations made on phase values or line values are equivalent, means line voltage per unit value is equals to phase voltage per unit value, line voltage current value is equals to phase voltage current value. So with using per unit system we can avoid this big confusion as well, okay. So per unit system is one such topic and these are the important formulas. Then symmetrical component, okay. So what are the symmetrical components? So first of all we have to understand the balanced and unbalanced system. So what do we mean by balanced system? If suppose we have three phases, this is R phase, this is Y phase and this one is the B phase, okay. And if all the voltages are displaced 120 degree exactly from each other, then this is a set of balanced system, okay. If you will see from any of the phases, the system appears to be symmetrical, okay. But if suppose we have system like this is R phase and let us suppose this is the Y phase and we have this as the B phase. Now whether we have 120 degree phase relationship between them? No, okay. So this is called as unbalanced system. Phase system does not appears to be same if it is viewed from any of the phases. So with the balanced system, analysis can be made on per phase basis. With an unbalanced system, analysis cannot be made on per phase basis. So that's why we need to convert unbalanced system into some balanced kind of approach for the analysis purpose, and we did this particular thing by assuming that if suppose we have unbalanced system, then we can resolve an unbalanced phasor into three sets of balanced phasor, in which we have zero sequence component, positive sequence component and the negative sequence component for every phase. Similarly we can do for Y phase as well, Vy0 plus Vy1 plus Vy2. Similarly we can do it for B phase, so it will be B0, B1 and then B2, okay. So just see what is this. This represent the zero sequence component, okay. This is called as the zero sequence component. Why they are called zero sequence component? Because there is no phase displacement with respect to each other. They all are equal in magnitude, but there is no phase displacement with respect to each other. Then we have another set of phasors which are called as the positive sequence component. These are known as the positive sequence component. Why they are called as positive sequence component? Because they all are equal in magnitude, but they are having the same phase sequence as the original unbalanced phasor is having, okay. So same phase sequence. That is why they are also called as positive sequence component. And then we have third set of component which are known as the negative sequence component. And why they are called as negative phase sequence component? Just because of the phase sequence is opposite, okay. They are having the opposite phase sequence with respect to original unbalanced phasor, okay. So there is no phase sequence in zero sequence component, all are equal. In positive, if this is RYB phase sequence, they will be having the same RYB phase sequence and they will be balanced as well. Then another balanced but opposite phase sequence component, if suppose this is RYB, then they might be having RBY, so negative phase sequence component, okay. Now positive and negative sequence component, they are balanced, okay, while the original unbalanced phasor, it is unbalanced. Okay, so what we have done, if suppose we have unbalanced system, we can resolve that unbalanced system into 3 sets of balanced phasors, positive, negative and zero sequence component. Okay, so this is how we will be able to resolve one of the biggest problem. Okay, if we have balanced system, analysis can be made on per phase basis. There is no problem because system is symmetrical. But if we have unbalanced system, we can't do like that. So we need to find some approach, and this is what we have done. Okay. So this is balanced and unbalanced system and symmetrical component. Now symmetrical component and their component synthesis. So guys, in how to transform an unbalanced phasors into 3 sets of balanced phasors. So for that we have some matrix transformation, and we can do it with the help of this matrix transformation. If suppose we have 3 sets of unbalanced phasor VR, Vy and Vb, then we can use a matrix which is like this. Alpha is an operator, and we can resolve it into zero, positive and negative sequence component. Now we have done it for R phase. Now if we have done for R phase, we can calculate for other phases as well. Okay. If suppose you know that what is the value of VR1, if the VR1 value is known to you, you can calculate the value of Vy1 using this formula, alpha square VR1. You can calculate the value of Vb2 by using this formula, alpha times VR1. Similarly, if you know the value of VR2, you can calculate the value of Vy2 by using this formula, alpha times VR2, and you can calculate the value of Vb2 by using this formula, alpha times VR2, and you know that VR0, Vy0 and Vb0, they all are equal to each other. Okay. Now if suppose you want to do the reverse, if suppose we want to find out VR0, VR1 and VR2, then we will just take the inverse of this matrix and we can find out the same as well. So it will be 1 by 3, 1, 1, 1, 1, alpha and alpha square, they will exchange their places, and now we will be having here VR, Vy and Vb. So you can see here, if the sequence components are known to you, you can also find out the original unbalanced phasors as well. Okay. Now what is this alpha? So alpha is an operator which is one angle 120 degree or minus 0.5 plus j 0.866. Similarly, alpha square is either one angle minus 120 degree, or you can write one angle 240 degree, or the value is minus 0.5 minus j 0.866. And then we have a relation 1 plus alpha square, this is equals to 0. If suppose you are interested in finding the alpha conjugate, means one angle 120 conjugate, so it will be one angle minus 120 degree, which is nothing but the alpha square, isn't it? And similarly we have alpha minus alpha square, this is equals to j root 3. Okay. So these all are the important points regarding the alpha operator and how to transform the sequence component from original unbalanced phasor, and how to get the original unbalanced phasor back from the sequence component. By using this you can do it. Okay. Now let me ask you a question. If suppose the system is balanced, then what will happen? If the system is balanced, so for a balanced system, there is no zero sequence current. Okay, if I talk about any phasor, there is no negative sequence component, and we have only positive sequence component present, which is equal to the original balanced phasor. Okay. So in a balanced system, there is no negative and zero sequence component, only positive sequence component will be there, which is nothing but the original balanced system. Okay. So we will be doing all this analysis with the unbalanced system only. Now, if suppose you have an unbalanced system, so negative and positive sequence component will be there, but with zero sequence component, if it has to be there, there are certain conditions. Okay. And what are those conditions? So nature of zero sequence current. No zero sequence current can flow in the lines connected to a delta connected system. If suppose we have a delta connected system, let me make a delta connected system. So just see, this is a delta connected system. So in a delta connected system, zero sequence currents can flow in the windings. Okay, you can have zero sequence current in the windings, but there is no zero sequence current flowing in the lines. Okay, like this. So in delta connected system, because of the absence of written path, there is no zero sequence current flowing in the line. Okay, so how we will be showing this? The equivalent circuit of this might be shown to you like this. This is zero potential bus like reference, and just see, there is no interconnection with the line, and we are only having the zero sequence component. We will be showing like this, and just see, we are showing it with open circuit here. Can you see it? So this will be the equivalent circuit here. Zero sequence current are flowing in the windings, but there is no zero sequence current in the lines. So we are showing it with open circuit. Okay. Now second point is, zero sequence current can flow in the lines connected to star connected system if neutral or ground return is present. If it is a star connected system and with there is no neutral present, again there will not be any zero sequence current flowing. But if the neutral is present, we can have zero sequence current. So if suppose we have a star connected system, like this. If suppose we have a star connected system, and if there is no ground or neutral present, there will not be any zero sequence current flowing. But if suppose we have ground present here, okay, let us suppose it is grounded solidly, or let me take an impedance. Okay, I am taking it to be x of n. So if ground return is available, there will be zero sequence current flowing, and we will show this diagram with this. So we have the zero sequence impedance, and this impedance of neutral might be represented by 3Zn. Okay, so just see, this is ZPB, zero potential bus, and this is how you will show it. Okay, so equivalent Z0 will be what? It will be Z0 plus 3Zn if neutral is present and it is having some reactance. Okay, if it is not having any reactance, this will be a direct short here. So Z0 will only be Z0. Okay, there is no 3Zn there. So this is, you should know about zero sequence current. So zero sequence current, they will be flowing if there is a return path available. If there is no return path available, we will not talk about the zero sequence current. It will be having a zero value. Okay, and we will not be talking about the positive and negative sequence component. There is no such discussion. If it is an unbalanced system, they will exist. If it is not a, if it is a balanced system, no negative sequence as well, no zero sequence component as well. But with zero sequence component, if we are talking about it, we will also see that whether there is a ground return or neutral available or not. Okay. Now sequence impedances. So we have sequence voltages, sequence current. So obviously we will be having sequence impedance as well. So sequence impedance. So we have positive sequence impedance and the positive sequence impedance denoted by Z1, and this will be equals to positive sequence voltage, ratio of positive sequence voltage to the positive sequence current. Similarly, we will be having negative sequence impedance and the negative sequence impedance is denoted by Z2, and this will be the ratio of negative sequence voltage to the negative sequence current. Okay. Now all these impedances, normally in power system, the resistance of the line is negligible as compared to the reactance. So obviously they all will be having a reactance value. Then we have zero sequence impedance. So zero sequence impedance Z0, it will be the ratio of zero sequence voltage to the zero sequence current. If zero sequence current is not flowing, this impedance will be infinite, and that place will be denoted by an open circuit, isn't it? So it is very much visible here. Now these are the positive, negative and zero sequence component. Now what are their values for different machines. Okay, so if suppose we have static devices, static devices means the transmission lines and the transformer. Okay, so for static devices, if we talk about the transmission lines, so for transmission line Z1 is equal to Z2, but it is less than Z0. Okay, and we have some specific values as well. Z1 and equal to Z2, this is equals to Zs minus Zm. Zs is the self impedance of the line, Zm is the mutual impedance between the lines, and Z0 it is having the highest value, which is Zs plus 2Zm. Okay, Zs plus 2Zm. And if suppose we have transformers, okay, then for transformer Z1 is equals to Z2 and they are greater than Z0. Okay, and if suppose we have dynamic devices, if we have dynamic devices means alternator or generator, then we have a relationship between these impedances like Z1 is greater than Z2 is greater than Z0. Okay, now this page which is open in front of you right now is a very important page. So many times there has been a question in the GATE exam from all these data. So if you know this data, surely you are prepared with one GATE question. Okay, so this is very important. So which of the devices are having highest value for zero sequence impedance? It is the transmission line. Okay, now sequence network. So if voltage is existing, current is existing, impedance is existing, obviously there will be some network as well. So if we talk about sequence network, so for positive sequence network, so the positive sequence network, it will be shown like this. We will be having an EMF, okay, and we will be having some reactance or impedance Z1, okay, and this will be the positive sequence voltage, and here is the current, positive sequence current which is flowing. So if we apply the KVL here, VR1 it will be equals to E minus I of R1 Z1. Okay, so this is regarding positive sequence network. Now if we talk about negative sequence network, so in negative sequence network we will not be showing any voltage, only there will be an impedance, current and the negative sequence voltage VR2, this is Z2 and this will be IR2. So what will be the KVL? VR2 will be minus of IR2 and Z2. Okay, so this is the negative sequence component network. Then for zero sequence network, again we will be showing it similarly what we have done in negative sequence. So there will not be any voltage source, only impedance, voltage and currents will be there. So what will be VR0? It will be minus of IR0 and Z0. Okay, so these are the three sequence network. Why we only have voltage in positive sequence and it disappears in negative and zero sequence network? If suppose we have an alternator and it is rotating in clockwise direction, in order to replicate the negative sequence component, immediately you have to suppose that your alternator is rotating in anti-clockwise direction. Is it possible? A clockwise rotating alternator cannot immediately rotate in anti-clockwise direction. So the voltage induced due to negative sequence component will be 0. So that's why there is no voltage shown here. Similarly for that, and clockwise rotating alternator suddenly it has to come into rest, which is impossible, isn't it? So that's why for zero sequence network there is no induced voltage we are showing. Okay, so these are the sequence network. Now zero sequence network of transformer, very important topic. With transformer, the negative and positive sequence component or the impedance will be treated normally, but with zero sequence network of transformer, there are certain conditions imposed. It depends upon what type of connection we have at the primary and at the secondary. Okay. So, in order to replicate the zero sequence network or transformer, we have this switch diagram. So, we have primary switches 1 and 2, and we have secondary switches 1 dash and 2 dash, and in between we have zero sequence impedance. Okay. So, switch number 1 and 2, switch number 1 and 1 dash, they will be closed if the side, respective side is star connected, grounded. Okay, star connected with ground return. Okay, and 2 and 2 dash, they will be closed if that side is delta connected. They will be closed if the side is simply delta connected. Okay. For example, let me take an example. If suppose we have delta star grounded, and let me call this to be xn. If suppose primary and secondary sides are connected like this, then what will happen? If when it comes to 1 and 2, 1 will be open because that side is delta connected, only 2 will be closed at the primary side. So, how we will be showing this? At the primary, 1 will be open and 2 will be closed. Okay. And then we have x naught. Now, talk about the secondary side. So, 2 dash will be open because that side is not delta connected. Okay. So, 2 dash will be open and 1 dash will be closed because that side is star connected, and not only star connected, with ground return as well. So, what you will do? We will replace this reactance with 3 of xn. So, now this will be the sequence network. So, what will be the Z naught? It will be x naught plus 3xn. Just see. This is what you have to do. Okay. So, this switch diagram is very important when it comes to the zero sequence network of transformer. Okay. We will be closing or opening that particular side depending upon what we have written here. 1 and 1 dash, they will be closed if that particular side is star connected with ground return. 2 and 2 dash will be closed if that side is delta connected. Okay. So, this is regarding zero sequence network of transformer. Now, symmetrical fault analysis. Now, let us jump into fault analysis. Symmetrical fault analysis. So, with fault analysis, let me tell you some fact. A short circuit or fault is high current, low voltage and highly inductive, low power factor phenomena. If there will be a short or fault any place, voltage will be very low, current will be very high, and since complete power system network, we are assuming reactance is only there, resistance is negligible. So, it is highly lagging power factor phenomena and very low power factor phenomena. Okay. During the time of fault, there is huge demand of reactive power and active power may become 0. Okay. So, these are the facts you should know about the faults. Whenever there will be a fault, you will always find these 2 points. Okay. Now, symmetrical fault analysis means under these faults, the system remains balanced. Okay. The balanced nature of the system is always there. Okay. Now, how to do the symmetrical fault analysis? So, we have some procedure to conduct symmetrical fault analysis. If suppose wherever is the fault point, what you have to do is, with respect to that fault point and the zero potential bus, you have to convert your network into a Thevenin's equivalent network. Okay. So, we have written this here. Convert the single line diagram of power system network into per unit reactance diagram. So, first you will be converting that into per unit reactance diagram. Then look for the faulted bus terminal and ZPB. You have to look for the fault point and the zero potential bus and reduce the network into Thevenin's equivalent network. Okay. So, when you will be reducing the network into Thevenin's equivalent network, so in Thevenin's equivalent network, we have only 2 things, Thevenin's voltage and Thevenin's reactance or impedance. So, just see, you will get after doing this Thevenin's voltage and Thevenin's impedance. Okay. Now, these are the short fault points. Just see, this is like zero potential bus, and this is your fault point. So, with respect to the fault point and zero potential bus, you have converted the whole network into a Thevenin's equivalent network. Now, if suppose we have shorted this network, so if suppose you have to calculate the short circuit current or fault current, this simply will be equals to E upon XTH, okay, E upon XTH, and E is normally taken to be 1 per unit. So, 1 upon XTH will be the fault current. Now, we have to choose the rating of circuit breaker. We have to install the circuit breaker so that circuit breaker can interrupt the circuit. They can isolate the faulty and the healthy section, okay. Now, the question arises, what rating of circuit breaker has to be chosen? So, they are chosen as per the rating of the fault current, okay. So, if rating of circuit breaker you have to choose, this is equals to the fault current into the system base, okay. Fault current into the system base, or you can modify this to be E upon XTH into S base. This will be the formula. So, the circuit breaker will be chosen depending upon the magnitude of the fault current, okay. Now, if this fault current is very high, you have to limit this unless there it can cause so much damage. So, this we will be doing by inserting series reactance in this network, okay. So, then your fault current will become E upon XTH plus XE. So, this fault current is now reduced, okay. So, if you have inserted the series reactance, fault current will be less, ultimately the circuit breaker rating will be low as well. So, you can choose low circuit breaker, low rating circuit breaker as well, okay. So, what we have learned is, while symmetrical fault analysis, we have to just convert our equivalent network into a Thevenin's equivalent network with respect to the faulty point and the zero potential bus. E, the system voltage normally will be chosen as base voltage. So, E we can take 1. So, what do we require? We require the value of Thevenin's equivalent reactance. So, you have to utilize your network skill in finding the Thevenin's equivalent reactance as Thevenin's equivalent reactance between the nodes of faulted point and zero potential bus, okay. If you are very much aware of this, how to find Thevenin's equivalent reactance, you can very easily calculate symmetrical fault problems, okay. Now, coming to unsymmetrical fault analysis. Unsymmetrical means, if the fault will occur, the system will not be a balanced system, it will become unbalanced system. So, there will be positive, negative and zero sequence components existing, okay. Now, when it comes to unsymmetrical faults, we can divide these faults into several categories. So, first among them is single line to ground fault. So, what you can see, there were 3 phases and only one phase somehow comes into the contact of ground, or suppose one wire is only getting a fault, okay. So, single line to ground fault, what will happen? Earlier we have all the currents flowing, but now what will happen? Your R phase current will be equals to the fault current, and IY current and IB current will be 0. This is the boundary condition that you have, okay. And if single line to ground fault is there, all the sequence currents, they are equal to each other. IR0, IR1 and IR2, positive, negative and zero sequence component of currents are equal to each other. If currents are equal to each other, this signifies that their sequence networks are connected in series, otherwise this is not possible, isn't it? So, you can see positive, negative, zero sequence network, they are connected in series, okay. Only then we can have the same current, okay. So, just see, this is the equivalent network of single line to ground fault. Now, if I have to find what will be the value of IR1 from this diagram, this will be simply E upon Z1 plus Z2 plus Z0 plus 3 ZF. ZF is the fault impedance. If this is not given, we will not write it, okay. And if suppose sometimes instead of ZF, say they are giving the value of Zn. So, if Zn is given, neutral impedance is given, you will draw that neutral impedance here. X0 will not be drawn alone, it will be drawn with X0 plus 3Xn. So, that 3Xn will also come here, okay. Now how to calculate the fault current? So line to ground fault current, this is equals to 3 times any of the current, IR1, IR2 or IR0, because they are all equal. So the fault current formula will become 3E upon Z1 plus Z2 plus Z0 plus 3ZF. Okay, so this is the line to ground fault current. So these are the important formulas you should know regarding line to ground fault current, and sequence currents are equal. Sequence networks are connected in series. This is what you should be knowing about line to ground fault. Next fault that we have is line to line fault, double line fault. So what you can see, two lines are getting in contact with each other. Okay, so what will happen, since nothing is happening with IR, so we can, IR will be 0, and just see these are the currents IR, IY, and here we have IB. So IR will be 0 and IY will be equals to minus of IB. Okay. Now what will happen here, just see, one thing is sure, there is no ground return available, so zero sequence current will be 0, isn't it? There is no ground return available, so zero sequence current will be equal to 0. Now if you will use the component synthesis matrix, okay, you will get IR1 equal to minus of IR2. IR1 will be equals to minus of IR2. Positive and negative sequence currents are equal but opposite to each other. Now if this is the case, their networks has to be connected back to back with respect to each other, only then we can have IR1 equals to minus of IR2. Yes or no, isn't it? So just see, the networks are connected back to back with respect to each other. Now if suppose I have to find what will be the value of IR1 here, then IR1 will be equals to E upon Z1 plus Z2 plus ZF. Okay, and the fault current in case of line to line fault, this is equals to root 3 times IR1. Okay, I am talking about the magnitude. So it will be equals to root 3 E upon Z1 plus Z2 plus ZF. Okay, so just see, these are the important formulas related to the line to line fault. Okay, how to identify, this is what you have to do. Similarly, in line to ground fault, how to identify it is a line to ground fault, by looking into the current values you can do that. Okay, next fault is double line to ground fault. So what is the difference? Two lines are getting in contact and then finally they are getting in contact with the ground as well. Okay, so what will happen? IR will be 0 and now we will be having IY plus IB, this is constituting to the fault current. Okay. Now what do we have here? By putting all these conditions, you will get that IR0 plus IR1 plus IR2 is equal to 0 here. Okay, the summation of three currents are equal to 0. Now if we have the sum of three currents equal to 0, only possibility is to have this network. All the networks are connected in parallel with respect to each other, isn't it? Without this network, is it possible that we can have this summation of current to be equal to 0? No. Okay, so IR1 current is coming here, IR2 current is coming here, and IR0 is coming from 0 sequence network, and their summation is equals to 0. Okay. Also we have the three sequence voltages VR0, VR1 and VR2, they are also equal to each other. Now if suppose you have to find out the value of IR1, so this will be equals to the system voltage divided by the total impedance. Total impedance is basically Z1 plus the parallel combination of these two impedances. Okay, so the parallel combination of this is Z of 2. So parallel combination of Z2 plus Z0 plus 3ZF. Okay, this is IR1. Now how to find out the value of other currents? So if you want to calculate IR2, you can use the current divider rule. So it will be minus of IR1, minus because of the directions are opposite, divided by, now we are finding IR1, sorry IR2. So we have to take the opposite impedance Z0 plus 3ZF divided by the total impedance, which is Z0 plus 3ZF plus Z2. Similarly, you can find out IR2 as well. Okay. So, these are the important formulas related to double line to ground fault. What are the important things? This condition, summation of all the current equal to 0. Okay. So, this is double line to ground fault. Now, triple L or three phase faults, kind of symmetrical fault. Okay. So, in this what will happen, since it is a triple L fault, symmetrical fault, what are the important conditions? We will be having IR0 0, we will be having IR2 0, only IR1 will be there, and that is my fault current here. Okay, that is my fault current here. So, since it is a triple L fault, symmetrical fault, there will not be any scope for zero sequence and negative sequence components. So, only positive sequence component will be there. So, this is the positive sequence network. Now, if we have to find out what will be the value of IR1 here or the fault current, so this will be equals to E upon Z1 plus ZF. This is how you have to find out the fault current here. Okay, so this is a very simple case, isn't it? So these all are the faults. Now comparison of three phase and line to ground fault, this is very important. So we have certain cases here. Let me choose case number 1, and which is if generator neutral is solidly grounded. Solidly grounded means Xn value is 0. Okay, so we have this condition. Just see, we have generator neutral which is solidly grounded. So if this is the case, in this case, the line to ground fault current is much more severe than the three phase fault current. So if you are choosing the circuit breaker in such a situation, choose it on the basis of line to ground fault, not on the basis of three phase fault, because you are going to make a wrong choice then. Okay, because line to ground fault is more severe, it will be having more value as compared to three phase fault. So choose the circuit breaker as per the rating of line to ground fault. Okay. Now let me discuss the second case. So in case number 2, what do we have? In case number 2, if let us suppose Xn is not equal to 0, means generator neutral is grounded with some reactance. Okay, then we have certain conditions. Now Xn, if it is equal to 1 by 3 of X1 minus X0, in that case both the fault currents are equal to each other. Okay, both are severe. Now if suppose this is having a value less than 1 by 3 of X1 minus X0, in that case the line to ground fault current will be more severe than the three phase fault current. Okay. Now if this is greater than this value, then line to ground fault current is less severe and three phase fault current will be more severe, and you will choose the circuit breaker as per the rating of the three phase fault current. Okay. Now sometimes in gate the question is asked, if line to ground fault and three phase fault currents are equal to each other, what is the value of reactance that we will insert? So you will simply calculate it, Xn equals to 1 by 3 X1 minus X0, isn't it? Sometimes it is right, sometimes it is wrong, because all this analysis is perfect if X1 is having a value of X2. So if X1 is equals to X2, you can directly calculate the reactance value by using this formula. If X1 is not equal to X2, don't use this formula, otherwise just apply the condition line to ground fault current, three phase fault current, and use their respective formula and you will get the value of Xn. Okay, numerically calculate that. Okay, so be very vigilant with this condition and when we have to use this. Now Z bus impedance matrix. So in power system we have basically two matrices, Y bus matrix and Z bus matrix. So Y bus matrix, bus admittance matrix, is basically used for load flow analysis. Okay, and Z bus matrix is used for fault analysis. Okay. So what is Z bus matrix? You have this Z bus matrix. Let us suppose all the values here will be n. This is Zn1. Okay. N2, Nk, and Nn. So we have a Z bus matrix. Okay. Now if suppose we have to do certain modification in this matrix, how they can be done? So type 1 modification. In type 1 modification, what we are doing? We are having a power system network having n buses and one reference bus, and what is happening? A new bus is added to the reference bus. Okay. So just see, an element of value, let us suppose Zs. So an element of value Zs is added between a new bus and the existing reference bus of the system. So what will be the new bus matrix? So in that case, the Z bus new, that will be equals to Z bus old. Okay. So we will write the Z bus old matrix as it is. Okay. And everywhere in all the rows we will write, in complete row we will write 0, in complete row we will write 0, and here we will write only the element Z of S. Okay. So what has happened? Complete matrix is same, only one row and column has been added, and the order of matrix is increased by 1. N plus 1 into n plus 1. Okay. So this type 1 modification has increased the order of the matrix. This is what you have to do here. Okay. Type 2 modification. In type 2 modification, what we are doing? Now we are adding an element Z of S, okay, from a new bus to an existing bus of the system. This time we have changed the bus. Earlier we have chosen the reference bus. Now we are adding a systems bus. Okay. So if you are doing this, what will be the new bus matrix? So in that case, your Z bus new, this will be equals to Z bus old. Okay. And what you will be doing here? You will write in which bus you are adding element? K. Okay. So you will be writing the kth row here. Okay. ZK1, ZK2, and so on. Here you will be writing the kth column. So Z1K, Z2K, Z3K, and like that. And here you will be writing the diagonal element ZKK plus the new element that you are adding. Okay. Again you can see the order of the matrix is increased, n plus 1, n plus 1. Okay. So we are repeating the kth row here, we are repeating the kth column here, and this element will be the diagonal element of K plus Zs. Okay. What is K? K is the bus in which a new element is added from some bus coming out from the existing power system. Okay. So this is the type 2 modification. Now if suppose we have type 3 modification, there is no new bus, we are adding an element of Zs value between kth bus and the reference bus. In that case, what we will do? In that case, your Z bus new, that will be equals to Z bus old minus 1 upon. We are adding element between kth bus. So we will write here ZKK and the new element is Zs, and you will write here the Zth kth column. So Z1K, Z2K, and similarly Znk. Okay. And here you will write the kth row, ZK1, ZK2, and ZKN. Okay. So just see, this is how you will calculate your new bus matrix. Is it the order which is going to increase now? No, the order will remain the same. Okay. So the old bus minus 1 by ZKK plus Zs, you will choose the kth column, kth row, you will multiply them, and then you will divide each element by this factor. Then whatever matrix is coming, you will subtract that matrix from the old matrix, you will get the new bus matrix. Okay. So this is what we will be doing. Now type 4 modification. Type 4 modification is a special case of type 3 modification. Here what you will do? Now we are adding an element within 2 bus of the system. Okay, within 2 bus of the system we are adding an element. So what will be the case here? So in this case the Z bus new, this will be equals to Z bus old minus 1 by bus number I and K are involved. Okay, so ZII plus ZKK minus 2 of ZIK plus ZS, the element which is going to be added. And now we will subtract the elements of ith and kth column. Okay, so Z1I minus Z1K, Z2I minus Z2K, similarly Zni minus Znk. So we have subtracted the columns. Now we will subtract the rows of I and K bus. So Z1I minus Z1K, Z2I minus Z2K. Okay, like that we will be writing all elements, and finally Zni minus Znk. Okay, so what we are doing here, subtract I and K columns, and what we are doing here, subtract I and K rows. Okay, like that we are doing here. So this is how these 4 modification will be done and new matrix will be formed. Now analysis using Z bus. If suppose you have to calculate a fault, if suppose we have 2 buses here, okay, if suppose we have 2 buses, bus number 1, bus number 2, okay, this is having V1 voltage, this is having V2 voltage, element connected between them is Z12, okay. If suppose the fault is, and you know the Z bus matrix, if fault is at bus 1, you will calculate the fault current using bus 1 voltage divided by the bus 1 impedance Z11, and if suppose there is a fault impedance added, you will add that as well. Okay. If suppose the fault is at bus 2, then how you will calculate the fault current? You will choose the bus 2 voltage divided by Z22 plus fault impedance. So wherever the fault is taking place, you will use that diagonal element. Okay. This is how you will calculate the fault current. Now if suppose fault is happening at bus number 1 and you have to calculate the bus number 2 voltage. So V2 post fault, this will be equals to V1, this will be equals to V2 pre-fault minus the fault current, okay, and Z12. Okay. The fault current you will use with respect to where the fault is happening. Okay. Similarly, you can write it for V1 as well. V1 post fault, this will be equals to V1 pre-fault minus fault current and Z12. Now fault current you will write as per where the fault is happening. If the fault is at 1, you will write, you will use this formula. Okay. If fault is at bus 2, you will use this formula. Okay. So this is how, with the help of Z bus matrix, the fault analysis and fault calculation will be done. Okay. So this is all about the fault analysis. Now let's move on into load flow analysis chapter. Okay. So what are the important topics? Classification of bus, bus admittance matrix, Jacobian matrix, economic load dispatch. Classification of bus. So buses are classified into 3 categories: PV bus, generator bus, PQ bus, load bus, slack bus or reference bus. So what are the known and unknown quantities? If we have PV bus, the known quantities are active power and the voltage magnitude. Unknown quantities are the voltage angle and the reactive power. If we have load bus or PQ bus, known quantities are active and reactive power. Unknown quantities are voltage magnitude and its angle. if we have slack bus or reference bus, okay. So what is that slack bus or reference bus? When we are commissioning the power system, okay, we don't know how much losses are taking place in the system because load flow analysis is not yet completed. When we will be able to complete that, we will be having the complete information. So when we are commissioning the system, somebody has to supply the losses taking place in the power system, yes or no, isn't it? We don't know how much losses are taking place, but we are very sure that losses are taking place. Somebody has to supply those losses. Now who will take that responsibility? So one of the generator bus, one of the PV bus, it will take the responsibility of supplying that additional losses. So it will be chosen as the reference bus. Now since it is chosen as the reference bus, we know the value of del, which is normally 0, isn't it? Which is normally 0. And the biggest generator of the power system will normally chosen as the reference bus, okay, and its voltage will be chosen as 1 per unit. So we know the voltage rating of it as well. So what is unknown? Even though this bus is supplying the losses, but we don't know how much. So that's why the unknown quantities are P and Q, active and reactive power, okay. So with respect to slack or reference bus, one of the generator buses will be acting as a slack bus, and that's why while calculating the Jacobian matrix we used to subtract 1, because out of all the generator bus, one of them will be acting as a slack bus or reference bus. Since it is a reference bus, del and V are known, okay, and P and Q are unknown. So this is the classification of buses. Now bus admittance matrix. So if suppose we have a system of buses, okay, some of them will be connected with respect to each other, some of them have no connection, okay. So if we want to analyze the load flow analysis, if we want to calculate what is the power at buses, what is the voltage magnitude, what are the currents flowing, we need to have something, isn't it, that correlates all the buses of the power system, and Y bus matrix is something like that, okay. So Y bus matrix, Y bus admittance matrix, you know that I is equals to V upon Z, or 1 by Z is basically Y, okay. So I is equals to V into Y, where what is Y? Y is basically admittance, the reversal of impedance, okay. So we will be writing the KCL equation at the buses to calculate I, the total currents, and we will try to relate the total current, all the currents of the buses with all the voltages, and the coefficient used in relating those will be called as the bus admittance matrix. So you can see for this system in which bus number 1 is V1, bus number 1 is having voltage V1 and one generator is supplying current I1, bus number 2 is having voltage V2 and one of the generator is supplying current I2, bus number 3 is having a load connected having bus voltage V3 and load is drawing a current of I3, okay. So this is your load bus or PQ bus. Now these are your generator bus, one of them you can choose as reference or slack bus, okay, and there is a shunt element connected here as well, okay. So we have calculated the Y bus matrix relating the currents of the system with the voltage, and we will get something like this. So in this you can see we have some diagonal element and we have some off diagonal element. So when it comes to diagonal element, if we talk about the diagonal element, just see what are the diagonal elements, how we have calculated that. So if we are calculating the diagonal element of bus number 1, what we will be doing? Y12 plus Y13. What is Y12? Y13 is basically 1 upon Z13. Y12 is basically 1 upon Z12. Similarly, Y23 will be 1 upon Z23. Okay. So if we are calculating Y11, add all the element connected to bus number 1. We are calculating Y22, add all the elements connected to bus number 2 and you will get Y22. If you want to calculate Y33, add all the elements connected to bus number 3. Okay, so this element and this element, and you will get diagonal element. So diagonal element of Y bus matrix is sum of all the elements connected to that bus. Okay. Now if you see any off diagonal element Y12, so Y12, if I have to calculate Y12, this is negative of the element connected between 1 and 2. Just see, this is how I am calculating all the off diagonal element. If two buses have no connection, the off diagonal element will be having a value 0. Okay. And in Y bus matrix there are so many such cases, and that's why Y bus matrix is also known as a sparse matrix. A matrix in which so many elements are 0 is known as a sparse matrix. So that is why Y bus matrix is also known as a sparse matrix. If so many elements of a matrix are 0, it will require less space, isn't it? So this is how you will calculate the Y bus matrix. What is the purpose, why we are doing so, what is the beauty of Y bus, we discuss all those things. Okay. Now few important thing related to Y bus matrix, and all these are very important point. Okay. The sum of all row element of ith is equal to the value of shunt admittance connected to bus I. Okay. So if you see just this problem, is there any shunt element connected here? No. Is there any shunt element connected here? No. So what will happen if you will simply sum the row? If you will simply sum up this row, okay. So if you are summing up the row, this will come out to be 0. That indicates there is no shunt element connected. If you will simply sum up the row number 2, you will again get 0. But if you will sum up the row number 3, so summation of row number 3 will give you Y3 naught, which is equals to the value of shunt element connected at bus number 3. So what shunt element is connected at bus number 3, you can determine by summing all the row elements. Okay, by summing all the row element. And also be aware of this thing, if we have impedance which is j omega L, this indicates an inductance. Okay. If we have Z equals to 1 upon j omega c or minus j upon omega c, this indicates a capacitance. Yes or no? But with admittance we will get minus of j upon omega L. Okay, minus of j upon omega L. So if minus j is coming, this indicates an inductance. Okay. Similarly, j omega c, if you are getting something like this, this indicates a capacitance. Okay. So not only you will be able to calculate the capacitance value, you will be able to calculate the shunt element value, you will be able to tell the nature of it as well. With inductance, if j is positive, it is inductance. With admittance, if j is negative, it is inductance. With capacitance, if j is negative, it is capacitance. With impedance, if j is negative, it is capacitance. With admittance, if j is positive, it is capacitance. Okay. Now sparsity, as we are saying that so many elements of Y bus matrix are 0, and that is the beauty of it. So how to calculate that sparsity? So percentage sparsity, this is equals to number of 0 elements divided by total number of elements. Okay. So if 4 zeros are there and it is 4 cross 4 matrix, so what will be there? 4 by 16 are the total elements. So you will get 25% sparsity. Okay. Number of transmission lines can also be calculated, which is equals to n square 1 minus x minus n by 2. What is n? Order of the matrix. What is x? Is sparsity. Okay. So you can calculate also how many number of transmission lines are there. Number of non-zero elements, this is equals to number of diagonal elements plus 2 into number of transmission lines. All these are very important formulas related to Y bus matrix. Okay. Now if suppose we have a transformer in between two buses, then there is a problem. We can't directly calculate the Y bus matrix just by inspection. So if suppose we have a transformer with transformation ratio 1:a, then the corresponding Y bus matrix will be a square y, y minus ay and minus ay. So what is the diagonal element? Y11 a square y. What is the diagonal element Y22? Simply y. And what is the off diagonal element? minus of minus ay, so we will get ay. Okay. So this is the equivalent Y bus matrix if we have transformer between the two buses, and we can draw the equivalent of it as well. So you can see we have two buses, and what is the off diagonal element? It is A into Y. Now what will be the shunt element connected to this bus? You will simply sum up this row. Okay. So if you will sum up this row, you will get this value. If you will sum up this row, you will get this value. Okay. So this network can be replaced by this network and the problem is solved. Okay. Now if suppose you have to find any specific element, or you have to find the complete Y bus matrix, you can very easily calculate that. Okay. So this is you should know. If suppose similarly we have two transformer with different ratios, one is 1:A, other is having B:A, then this is the equivalent Y bus matrix. Diagonal elements are A square Y and B square Y. Off diagonal elements are minus ABY minus ABY. Okay. So you should be aware of these things. Questions may be asked from this particular analysis. Then size of Jacobian matrix, one of the most important thing while Newton-Raphson method is being studied. Size of Jacobian matrix is 2n minus m minus 2 into 2n minus m minus 2. What is n? N is total number of buses. M is basically total number of PV buses, that includes voltage control buses, reactive power support buses, plus generator buses except slack bus. You will always subtract one from the generator buses. Okay. So sometimes directly PV buses are given, sometimes they are given with these names. So you all have to collect all these things to find out total number of PV buses. Okay. And sometimes this becomes even more easier if suppose number of PQ and PV buses are directly mentioned. You can use this formula as well, 2 times PQ buses plus PV buses. This is how you can calculate size of Jacobian matrix. Okay. Very important topic. So this is all about load flow analysis. Now economic load dispatch. So what is economic load dispatch? Economic load dispatch problem is basically an optimization problem. What is the objective? Objective is to allocate the plant load amongst the units in service in such a way that the total cost of generation is minimum. Okay. If suppose we have two generators, okay, one is having incremental cost of generation, means how many rupees we are wasting for generating 1 megawatt hour, incremental cost of generation. So one is having an incremental cost of generation of 60, other is having an incremental cost of generation is 100. Okay. Now if suppose some extra load is coming, which generator you will load first? If you will give more load to 100 generator, okay, if you will give more load to that generator which is having an incremental cost of 100, you will be wasting more money there, isn't it? But if you will load generator which is having incremental cost of 60 rupees per megawatt hour, and even if the cost of generation will increase, still it is not equal to the other one. Okay. So the purpose is, when the extra load is coming, we will not give the load to that particular generator which is already having very high cost of generation. Instead we will give that load to that generator which is having low cost of generation. Now other generators cost will increase, and when both the generators will be generating at the same cost, this is called as economic load dispatch. Okay. This is called as economic load dispatch. So economic load dispatch is basically concerned with the economics of the power system. There is no meaning of loading one generator more and other generator less if it is having less incremental cost. Okay. So the purpose is all the generators of the power system should produce equal incremental cost, and we will load the generators accordingly. This is the purpose of economic load dispatch. Very easy. Okay. Now in ELD problem there are two cases: considering losses, neglecting losses. So incremental cost of production dC1 upon dP1 of one generator, similarly of other generator, similarly of n generator, should be equals to lambda. Okay. Which is lambda is Lagrangian multiplier, rupees per megawatt hour is the unit of it, and the rupees per megawatt hour is the unit of this as well. and these are known as incremental cost of production. Okay. So, what it is saying that all the generators incremental cost of production should be equalized. This is how we will load the generator. Okay. Considering losses, this formula will become L1 dC1 upon dP1, L2 dC2 upon dP2, and similarly this is also equals to lambda. Okay. So, considering losses, the formula becomes same, so objective is still same. Now, what is this L1 and L2? They are called as penalty factor. How to calculate them? We will discuss. Okay. Now, loss equation. If suppose we are in such a scenario, we have two generating units. Okay. We have two generating units and they are sharing a load of PD. This is P1, this is P2. Generator 1 and generator 2. Then we have something called as loss equation, which is B11 P1 square, P22 P2 square plus 2 B12 P1 and P2, where B11, B22 and B12 they are loss coefficient and will be given in the problem. Okay, loss coefficient and will be given in the problem. Now, how to calculate L1 and L2? So, L1 is basically 1 upon 1 minus dou PL upon dou P1. Similarly, L2 is 1 upon 1 minus dou PL upon dou P2. Okay. L1 and L2 are penalty factors. Okay. So, this is how we have to do all those things. Okay. So, these are the important conditions, they will be given to you. You have to apply these two conditions and you should know what is L1 and L2. Okay. So, you will get in exam problems related to the same. Okay. So, this is part 1 and we will stop here. So, in this lecture today we discuss three important topics: fault analysis, per unit system, symmetrical component, the chapter name is fault analysis, then the load flow analysis, in which we discuss Y bus matrix, Jacobian matrix, classification of bus, and then this economic load dispatch. Okay. Now, we will meet tomorrow again and we will discuss further topics of power system. Okay. So, this is just an hour lecture and you have revised all these things. Now, PDF will be made available to you. Okay. And in this way you can do quickly the complete revision of power system in 3-4 hours. Okay. Revising power system, which has a very vast content, is not an easy task. Hello Jitendra, how are you? Okay. So, guys, we will meet tomorrow. In part 2 we will discuss some other topics, okay, like compensation techniques, okay, and some other topics we will discuss. Still so much things are left in power system. So, if you really like what we have covered in this lecture, you can, and you really like the teaching and learning methodology of IMS GATE Academy, you can join our live online program which has these many features. We are giving you 800 plus hours of live classes. We are giving you some exceptional material like theory book, exercise book, GATE questions bank, and one-to-one personalized sessions are also there, in which you can discuss with the faculties how to prepare for GATE exam and how to strategize subjects and so many things. We are also providing you 130 plus online test. Okay. So, guys, if you really want to join us, you can just call on these numbers. Sir, would you cover power system protection? Yes, Jitendra, I will cover everything. Okay. So, tomorrow will be power system part 2, in which we will cover some more topics, and then at Sunday we will be having another lecture in which we will cover power system protection as well. So, be there. Okay. Tomorrow we have the session at same time at 3 p.m. Sunday we have the session at 6 p.m. So, be there and we will do the revision of each and every chapter and topic. Okay. So, guys, you can call on this number and you can join IMS GATE Academy. We have a dedicated Telegram channel. The link of the Telegram channel is given in the description box. You can join our Telegram channel, okay, in which the lecture PDF will be given to you. Okay, Jitin, just join the Telegram channel. The PDF of this lecture will be given to you, and we are daily conducting some quizzes related to GATE. You will be having a flavor of that as well. And apart from that, if suppose some seminar, webinar and job notifications are coming, we are informing in that group as well. So you can join that group. It will be beneficial for you, okay. So thank you so much for attending this session. We will meet tomorrow at the same time, and we will discuss some other topics as well. Thank you so much.